to solve this linear system of equations is to find the coefficients of these vectors that will land me exactly at that target point, 10, 7. So we start by stretching out the vector v1. And as one of your groups explained yesterday, when you multiply a vector by a scalar, what do you end up doing to it? So here I'm multiplying the black vector v1 by some scalar and getting this red vector. What can you say about the relationship between a vector and its multiple? If I take v1 and I multiply it by, say, 2.
Well, if you multiply by a positive integer, then it just expands it.
Okay.
If you multiply by, or shrinks it, and if you expand it by a negative, it reflects it, and then expands and shrinks it.
Sure, right. So the multiple, scalar multiple of a vector, always either points in exactly the same direction as the vector, and is either longer or shorter depending on whether your positive number is bigger than 1 or less than 1, or it points in exactly the opposite direction, and is either longer or shorter depending on whether in absolute value that number is bigger than 1 or less than 1. The point is that it always is in the same direction, or if you like, it always lies on the same line that the original vector does. So when we multiply it by a constant, it lies on that same line. And so we stretch out our first basis vector by something. Here, let me try to be as accurate as I can be here. And then we stretch out our other vector by potentially something else. So stretch this out exactly as much as we need to land on our target point. And we find out, can't quite see the whole thing in this example, but we find out that the right combination of coefficients for this problem is that we need 3 of our first vector, 4, 1, and we need 2 of our second vector, negative 1, 2, and that combination actually hits our target vector 10, 7 right on the nose. So what that means is that the solution of our linear system was x equals 3, y equals 2. And you can check that that the original system of equations that was written down has that as a solution. So where we're going to push this to today, and we'll start with your reading responses in just a minute, but where we're going to push this to today is I want to take these vectors, these coefficients, C1, C2, or if you like, x and y. And instead of thinking of them as just coefficients in the sense that we can see on this app, what I'd like to do is I'd like to be able to take x and y and also package them into a vector. This is going to be today's goal, is to think about how this picture might change if we want to think of these coefficients, the solution, if you like, of our system of equations as also being a vector that has 2 components in it. So how is that going to require us to change our thinking a little bit? How does the picture change? And then how, when we think of x and y as a vector packaged together, how do we then understand what a linear system is asking us to do? And this is where the idea of a matrix and the arithmetic that you can do with matrices, specifically multiplication of matrices. This is where multiplication of matrices trots into the picture. Because matrix multiplication is completely defined and built around the idea that when I multiply a matrix by a vector, what I'm really doing is I'm selecting a linear combination of the columns of that matrix. So this linear combination that's happening in our equation that we're trying to solve, in our vector equation, gets replaced instead by matrix multiplication. So instead of linear combination, we end up with matrix multiplication. And the matrix that we multiply this vector by is exactly the matrix whose columns are 4, 1 and negative 1, 2. So this is going to be reframed today. Let me just carve out some space to finish this thought. That this equation, this linear combination, 3 times the vector 4, 1 plus 2 times the vector minus 1, 2, we're going to reimagine today in the following way. We're going to take these 2 vectors, negative 1, 2 and 4, 1, and make them the columns of a matrix Notice this is the same as the matrix of coefficients that we would have had for our linear system of equations. So we've seen this now in a couple different respects. Except that now, these will be in a matrix by themselves, instead of in the augmented matrix that we've been using previously to solve. And then we will be multiplying that matrix by the vector 3, 2. So that's the change in philosophy that we have here. That instead of a linear combination, 3 times the first vector plus 2 times the second vector, so 3 of these plus 2 of those, we're just going to rewrite it. And there's not a whole lot of meaning in this just yet. But we're going to rewrite it in this fashion, where when we multiply a matrix by a vector, we're saying, I'm going to take this many of the first column, and I'm going to add it to this many of the second column. So we're just putting it into a different wrapping, if you like. So we'll get a chance today to focus on how that changes our picture of what a linear system looks like. And then in the second phase today to go back to something we started talking about yesterday, and that is, well, what about for systems of equations that don't have a unique solution? How do we express the solution sets of those systems of equations? And hopefully today maybe also take a look at what do those solution sets look like. At least in the 2x2 case, we'll be able to see what a solution set to a linear system of equations looks like by the end of the hour.